To use totally unimodular matrices, we're going to embed problems as integer programs that have totally unimodular matrices as their constraint matrix. Our first example is going to be the min-cost flow problem. So far, we've modeled the shortest path problem and the maximum flow problem as a min-cost flow problem. So by embedding the minimum cost flow problem as a totally unimodular matrix problem, we're going to leverage all of the power of totally unimodular matrices to say things about min-cost flows. To show that the min-cost flow problem has a totally unimodular matrix, we're going to verify it directly by using one of our sets of sufficient conditions. In this case, we're going to use the first set. Here we have the constraints written for our min-cost flow problem. And here we have a particular instance of the min-cost flow problem. We're going to write out this matrix for this particular instance just to get an idea of what the properties are. In general, when looking at constraint matrices and verifying that they're totally unimodular, it's very helpful to write out a particular matrix for a small instance. In this case, the matrix is indexed by the variables for the edges 1, 2, 1, 3, 3, 2, and 2, 4. And the constraints are indexed by the vertices, in this case vertex 1, 2, 3, and 4. And now each one of these entries of this matrix correspond to some constant inside of our constraints up here. In particular, in the constraint for vertex 1, we see that the two arcs leaving 1 have to have a negative 1 associated with it. So we have a negative 1 for the arc 1, 2, and 1, 3. For the constraint for vertex 2, we have one arc coming into it, namely 1, 2, and we have two arcs leaving it, 3, 2, or 3, 2, and 2, 4. Sorry. For the constraint for vertex 3, we have one vertex coming in and one vertex leaving. And for the constraint for vertex 4, we have exactly one arc coming in. This is the specific matrix. Now we can prove that this matrix is totally unimodular. First, we verify that every entry in this matrix is 0, 1, or negative 1. We could have done this without even writing the matrix. The second is that we have at most two non-zeros in every column. This is easy to verify in the matrix that we wrote, but in general it's also easy to verify. Every arc has at most two nodes, so it's going to appear in at least two constraints. This means that there's going to be at most two non-zeros in every column, since columns correspond to arcs. Finally, we need to verify or partition the rows into two sets so that the sum of all the entries in one minus the sum of all the entries in others is 0. In this case, our two partitions are very easy. M1 is the set of all the rows, and M2 is the empty set. In this case, when we sum all the rows of the aij's, we have at least one positive 1 and one negative 1. So if we sum up all the entries in the row, we get 0. This is because every arc is going to appear exactly once as a negative and exactly once as a positive, because it's leaving one node and coming into another. Now we've verified all three conditions, and so the matrix for this min-cost flow problem is totally unimodular. As a result, solving the linear program provided that the vector, the right-hand side vector of dj's and uij's, is all integer, so will give us an integer solution to the linear program. The power of totally unimodular matrices comes from the fact that we can model so many problems as an integer program with a totally unimodular matrix. We've discussed the knapsack problem at length. Now we can make a generalization of it called the partition knapsack problem. In this generalization, we still have a set of items I, but we partition the items into k different sets, I1 through ik. Recall that our partition is a decomposition of our initial set, so that the partitions don't overlap, and the initial set can be written as a union of all of these sets in the partition. We're also going to have a set of capacities, Cj. The capacities now are not for a universal knapsack, but for the knapsack subject to a particular partition. All the items in partition 1, for example, have a capacity of at most C1. We also have a value for every item. The objective is to pick a set of items, K, so that we maximize the sum of the values in our knapsack subject to the different capacity in each one of the partitions. That is, each partition intersected with the items that we've chosen is at most Cj. We can model this partition knapsack problem as an integer program. The objective is the same as the knapsack objective. We're going to maximize the sum of the values of the items in our knapsack. The constraints now are a little bit different though. Instead of having a singular constraint, we have a constraint for each partition. That is, the sum of all the items, xi, in the partition, ij, is at most the capacity of the items assigned to that partition, cj. Here we've written the linear programming version, xi greater than or equal to 0. The reason why is because we're going to show that this constraint matrix is actually totally unimodular. And by writing the linear program, we know that the linear program is going to be equivalent to the integer program due to the total unimodularity. To show that the constraint matrix here is totally unimodular, we just take note of two facts. First, we note that the constraint matrix actually has two different sets. There's the constraints that are interesting, the ones that we wrote, that involve summing items over the partition, and these we're going to call A. There's also a set of constraints associated for each variable, but this is really just the identity matrix. And we know from our set of equivalences that A appended with the identity matrix is totally unimodular if and only if the original matrix A is totally unimodular. So all we need to do is show that the matrix A is totally unimodular. The identity matrix, in some sense, doesn't really make a difference. To do this, we're going to first write out what the structure of this matrix is. The matrix A has a 1, or a vector of 1s, for all the x variables in the particular partition. So if we look at the first row, we're going to have a 1 for all the x's, for all the items that are in the first partition. In the second row, we're going to have a 1 in every position for all the x's that are in the second partition, and so on until we get to the kth partition, where we have a 1 in every entry for all the x's in the kth partition. It's fairly simple to verify that this matrix is totally unimodular. In this case, we use the second set of conditions. First, we verify that every entry in this matrix is 0, 1, or -1. In this case, it's only 0s and 1s. Second, we verify that there's at most one non-zero in each column. This is trivial to verify, and if we needed to prove it, we would just identify that each one of these 1s occurs for exactly one item, and since the items are in a partition, there's at most 1 in each column. This verifies that this matrix is totally unimodular, and as a result, to solve the partition knapsack problem, we can write the linear program, solve the linear program, and then know that this linear program solution is going to be the same as the integer programming solution because the constraint matrix is totally unimodular.